Hello everyone, I'm Dan. In this tutorial I'm going to talk about basically the foundation of electronics here, the amperage and voltage. So to get started, go ahead and open up your web browser to my website, thegpu.com, and you can scroll down here to electronics tutorials or select menu electronics tutorials. Then we'll select voltage and amperage. So what is an amp? Well, atoms are comprised of protons, neutrons, and electrons. The protons and neutrons form the core of the atom, and the electrons orbit rapidly around the core, similar to the way our planets orbit around the sun. Electricity is the flow of spare electrons along things such as copper wire. Pure copper wire is comprised of atoms of copper. Imagine a strand of copper wire laying on a table. If an electron is added to one end of the wire, it bumps an electron from the first atom of the copper out of orbit. That electron then bumps another electron out of orbit from the next copper atom, which in turn bumps an electron out of orbit in the next copper atom, so on and so forth, repeating the cycle all the way down the wire. Now the term amp is simply short for ampere. Amperage is the measurement of the amount of electrons that flow through a point in 1 second. Now 1 amp is approximately equivalent to this giant number here, okay, of electrons passing through a point in 1 second. Now fractions of an amp are measured using the metric system, and you will quickly become familiar with the terms milliamps and microamps. So 1 amp is represented as this number of electrons passing through a certain point per second. Now a 100 milliamps is 1/10 of an amp, okay? 1 milliamp is 1,000th of an amp. But anyway, so 100 milliamps equals 1/10 of an amp. As you can see, that is basically this number reduced by the power of 10. So this many electrons pass through a certain point in 1 second at 100 milliamps. At 10 milliamps, right, now we're 100th of an amp, we're a 10th of a milliamp, and we're 10 times of a milliamp. So at 10 milliamps, this amount of electrons pass through a certain point every second. At 1 milliamp, we're at 1,000th of an amp. Okay, so an amp is 1,000 times more powerful than a milliamp, or a milliamp is 1/1,000th of as powerful as an amp. And we have this many electrons passing through a certain point per second. Now let's talk about microamps, okay? So 1 microamp is equivalent to, 1 milliamp is equivalent to 1,000 microamps. In other words, you need 1,000 microamps to equal 1 milliamp. And 100 microamps is equivalent to 1/10 of a milliamp. So we have this many electrons passing through a certain point every second. 10 microamps is 1/10 of 100 microamps, or 100th of a milliamp. And we have this many electrons passing through a certain point every second. Now, back down to the 1 microamp, which is about all you're really ever going to deal with, most likely. But who knows? I went a little further than that. But there's 1 million microamps in 1 amp. In other words, a microamp is 1/1,000,000th the power of an amp. Okay? And so there's this many electrons passing through a point every second. All right, so nanoamps, 100 nanoamps, 10 nanoamps, and 1 nanoamp, right? 1 nanoamp is 1/100000th of an amp. In other words, you need 1 billion nanoamps to equal 1 amp. And it's this many electrons passing through a point per second, okay? A milliamp is represented as lowercase ma, which, for example, this would be 150 milliamps. A microamp is represented as this little U symbol, A, right? This would be read 20 microamps, and a nanoamp is represented as N in the uppercase A. For example, 400 nanoamps. Okay, what is voltage? Now that we understand the concept of amperage, we need to figure out what could possibly cause all these electrons to move through a conductive material such as copper wire. Now, our eyes are incapable of seeing small things such as protons, neutrons, and electrons. While we accept that they are there, they are, for all intensive purposes, invisible. So we know that there is this invisible force that must be pushing the electrons down the wire, but what could it be? And the answer to that question is the term voltage. Now, voltage is just used to describe the potential force required to push electrons from one atom to another. The lower the voltage, the less force there is to push the electrons from one atom to another. Hence, less amperage is measured across the point when 1 second elapses. Now, conversely, the higher the voltage, the more force there is to push the electrons from one atom to another. Hence, more amperage is measured across a certain point when 1 second elapses. So there's a special relationship between amperage and voltage. Let's begin to explore how it works by frying an LED. Okay, I'm going to go ahead and pull up my little camera here. And what we're looking at is I've got, on Amazon, I just ordered this little assortment of LEDs, right? Various different colors. Essentially, this is like a data sheet right here. For example, the white ones that I'm going to be using, the white one that I've got wired up right down here, is a 20 milliamp is its rating, and 3 to 3.2 volts. And this is just how much light and what wavelength it produces right there. Don't worry about that. That's not actually part of the equation there, okay? So for example, like the yellow is only 2 to 2.2, so some of these have different specs. So that's what we're dealing with right here, the white one right down there. Over here is my Corad, and that's my DC linear power supply. I'll go over some, and I have two of them. The reason I have two of them is you can buy single DC linear power supplies with multiple outputs, but for me, it made a lot more sense. I don't know, the cost difference isn't too much versus buying two completely separate ones, and the advantages, in my opinion, are pretty significant. You know, if you fry one power supply, the other, you still have your backup there. Whereas if you fry a multi one, then your whole thing is dead in the water there. Also, you can do some interesting stuff with multiple circuits with the different power supplies there as well. It has a power button on it down here, and we'll go ahead and press that. Okay. It has a little on-off button right here, so nothing is happening. No current is getting sent to this until I actually press the on-off button right here. And I've got this dialed in, so volts up top here, 3 volts, and it will output a maximum current of 20 milliamps. Okay, so this is 1 amp. If it had a 1 over here with zeros, it'd be 100 milliamps. But this is the 10th slot, so this is 20 milliamps, which is 0.002 of an amp. Okay, and if I go ahead and press the on button here, lights up the LED, and we're well within specs. Now, what you'll notice is the voltage stayed the same here at 3 volts, and the amperage that it's actually drawing right now is between 18 and 19 milliamps. Okay, so a little less than the maximum 20 that we put out, right? And of course, the LED is consuming all those little electrons and outputting some light there. All right, let's run some experiments here. So I'm going to just press the off here, and I'm going to leave the amperage as a maximum of 0.20, but I can adjust the voltage up here by clicking this little button here. And I'm going to dial that down to 1 volt, and then I'm going to turn it on. Okay, so nothing's happening. This isn't lit up. We've got no amperage going through, and a maximum of 1 volt output there. Okay, so 1 volt is not even enough to push any amps across the little gap in the LED. If you've ever looked at these LEDs, there's a little gap in there, and doesn't even have enough voltage to push those across. So what I'm going to do, and it's still on, by the way. I'm just going to hit this right up here, and I'm going to scoot over to the 10th of a volt, and I am going to just start twisting this up. And at a certain point, we will get enough force, enough push to start pushing all those electrons across that little gap there. Okay? Oh, did you see? Okay, there we go. We've got just a slight bit of them flowing across, but we don't have... Oop, I lost my little thing there. Now we're starting to read all the electrons, the amperage that are actually passing through the LED at this point in time. Okay, so I'm going to just start cranking that down just a hair, right? So you can see at 2.9 volts, we only have enough, invisible force, voltage, right, to push just about 10 or 11 milliamps across there, right? If I turn this voltage down a little bit more to 2.8, right? Now 2.8 volts is that potential force. I only have enough force at that point in time to push 4 milliamps across here, okay? And if I crank that down to 2.7, right? The light is still on, but it's somewhere around 1 milliamp, and my this power supply here won't measure in microamps. However, I do have this cool thing that I bought on Amazon that does measure in microamps, but I'm not going to hook it up for this tutorial here. I will for future ones on this. All right, so one more notch down. We change this to 2.6 volts. There, we're registering 0. That doesn't mean that no amps are flowing across. That just means that my power supply can't measure the amps that are flowing through there. They're now in microamps. So my other thing could. Okay, so let's go ahead and just crank this up here. Okay. Now I'm gonna turn this off here. Okay, so I've got this set up for 3 volts, and the maximum amperage output is 20 milliamps. Okay, let's go ahead and actually I just want to turn this on here. Okay, so 3 volts, 18 milliamps. What happens if I keep going up a little bit there? 3.1, right? 2, and as I crank this up, this doesn't get any brighter. We haven't fried anything, and that's because even though we've got this super high push set up right here, 5.4 volts, 20 milliamps is our cap on the output there. Okay, so because that is our cap on the output, all of a sudden it's magic, right? It says, oh, okay, 3 volts is actually the amount of voltage or an amount of push that's pushing 19 milliamps through this LED. Okay, so you could kind of see the interesting relationship between the two. Now let's go ahead and do a little frying action here. Okay, as we know, let's go ahead and let's adjust this back down to 3 volts. Okay, and we're going to adjust this up to 30 milliamps. Okay, and then we're going to go ahead and hit on. Now, of course, our consumption still, because we've only got 3 volts of, I'm going to make this large here. We've only got 3 volts of potential pushing power, right? Pushing 18 milliamps through there. That's basically, even though I've got higher settings set to do 30, that's all that 3 volts can push through, right? Now I've got a higher setting going on here. If I increase the voltage, say, to 3.1, right? You can see now we've got 28 milliamps going through there. And, of course, my camera adjusts a little bit for the brightness on that. If I turn that back down, you can't really tell on the camera there, right? But at 3.3 volts, now we've got 29 going through. Okay, and at 3.5 volts, we've still got 3.1 going through there. All right, let's go ahead and get ready for some frying action here. Let's go ahead and burn this thing up. So we're gonna bump our voltage back down to 3 volts, and we are going to adjust the max amperage up to 1 amp. Okay, now right off the bat, we don't fry it, because of course 3 volts only has the pushing power to push 18 milliamps through there, right? But now, the power supply is going to output a maximum of 1 amp, and as we decrease this, right, the light's going to become dimmer. We're going to see the same thing going on there. But now, we've got some serious pushing power behind this thing. And you could see the LED is getting much brighter. Now the LED is starting to dim out there. Okay, at 5 volts, we're pushing 137 milliamps through. Let's keep cranking this thing up here. And boom. We just partially fried it. There's still a little bit of electricity flowing through there. It's just not producing visible light anymore. You might get some more flickers out of this thing. Oh, nope, it's now totally dead. Okay, so that just fried it. Okay, all right. I'm going to go ahead and cut the power to that and turn this off. And really, that'll about do it for this tutorial here. Hopefully, you guys got some stuff to think about there. But I'm going to go ahead and minimize that. And so basically just stay tuned for my next tutorial where I will explain how we can harness the relationship between amperage and voltage. That concludes this tutorial. Thanks for watching.